functions in cryptographic schemes.
Thanks. This is. I'm happy to give this talk. It's a kind of a very different talk from what I'm used to, because I'm kind of come more from the provable security side than from the side of attacking things. But it was a nice challenge to basically prepare this and try to give an overview of how to attack hash functions in post-quantum cryptographic schemes. So probably most of you know that hash functions are essentially everywhere in cryptography. So whether it's digital signatures or key establishment, or for example, encryption, public key encryption, basically all of these important functionalities are constructed using hash functions. And there's a number of others that are maybe not so present in that are not as widely used, or that are more like sub-primitives of that are used to construct the other ones. And one important question is, of course, whether we can use quantum algorithms to attack the use of hash functions in these cryptographic schemes. And this is what the talk will be about. So here's an outline. I will start by introducing hash functions. So this is kind of a mixed audience of quantum algorithms people and cryptographers. So I don't want to assume too much. So I will thoroughly introduce what a hash function is, its security properties, then quickly talk about the so-called random oracle model or its quantum variant, and also give an idea of how hash functions are actually constructed. After that, I will continue by kind of giving different meta strategies of how to attack hash functions. And subsequently, I will focus on one of them, which is attacking the use of hash functions in cryptographic schemes. So for this, I will introduce these two important generic transformations that are used in many cryptographic schemes that are competing in this NIST process, which are called Fiat Shamir transformation and Fujisaki Okamoto transformations. And then after that, I will talk about attacks or the lack thereof using quantum algorithms. Let's get started. So first of all, what is a hash function? A hash function is basically just a priori it's just a function, and it takes arbitrary length bit strings as an input, and then it maps these to a fixed length output. So what you can imagine that in practice we just take like some arbitrary amount of data and we map it to some small fingerprint or something like that. And basically the defining intuition for security is that a hash function should look random to somebody who has not, input the same string into the hash function before. There's a number of more concrete security properties that are informed by this intuition, and they include the ones that I've put here, but this is not an exhaustive list. So most importantly, there's one-wayness, which is the property that for a random image of this function, I cannot find a corresponding pre-image, and collision resistance, which says that I cannot find two inputs that map to the same output, and then a number of strengthenings of this, like, for example, collapsingness, which is a property that replaces collision resistance in the quantum setting if you use hash functions for commitments, for example, and a number more. Basically consistent with the fact that that these properties were defined by following our intuition that the function should look like a random function, an actual random function, has all these properties. And therefore, sometimes we resort to kind of fantasy world, which we call the random oracle model, where we just pretend that the hash function is, in fact, a random function. So I want to explain a bit more what this random oracle model is about. But before that, let me give an example application of hash functions. And that's the so-called hash and sign paradigm. So if you, first of all, what is a digital signature scheme? So here we have two players, Alice and Bob, and Alice wants to send a message to Bob. And she would like to ensure that this message is, arrives unaltered at Bob's and that Bob knows that it comes from her. So for this, she already earlier has generated a key pair where she has kept the secret key secret and to herself, and the public key she has published, and somehow established Bob's trust in this public key. So basically, Bob trusts that this public key belongs to Alice.
The key is in the cloud?
Yes, it's in the cloud. So now Alice can use the signing functionality to sign this message, generating a signature sigma, and send the pair m sigma to Bob. Bob can now use the verification function, which uses the public key only, to verify that this message indeed comes from Alice and is unaltered. Now, signature schemes are pretty inefficient compared to hash functions. So therefore, one can use the hash and sign paradigm by choosing an appropriate hash function with large enough codomain, and then hashing the message before signing. And this is a very good idea because it saves some computation, because the signing function is very computation intensive, and it should not harm security as long as the hash function is collision resistant. In this case, collision resistance is enough, and the hash function has a large enough output. So yeah, so this was just an illustrative example of a use of hash functions. So let's move on to a bit more information about this quantum random oracle model. So here we really pretend that the hash function is a random function, and a random function is, of course, you cannot efficiently specify it. So we just have to assume that everybody has oracle access, so input-output access to this hash function, to this random function h. And to kind of keep at least some connection to reality, in the case where we are talking about quantum attackers, we need to assume that everybody has quantum oracle access to this function, right? Because in reality, we're dealing with a concrete function. Everybody can implement it on their quantum computers if they have one. So we should at least allow, quantum evaluation of this random function if we model our concrete function as such. This is the so-called quantum random oracle model, and it was introduced by some people, including Chris Schaffner, who's here. And just to be a bit more concrete, so this is basically the standard unitary implementation of a classical function, and this is basically the functionality that we assume everybody in the world has access to for a random function h. This has been very successful because it has enabled provable security for very efficient schemes. But it has a downside because it's not the real world. Like we are pretending that it's a random function while it's not, and this is a fact that actually allows for vulnerabilities in principle, which I will talk about a bit more later. So now a bit more about the construction of hash functions. So we want a hash function, this object with arbitrary length input, but that's kind of a bit of an unwielding object because we are supposed to basically evaluate it on any length string, so on this infinite domain. So what's much easier is to construct a fixed domain, a fixed length domain function that has similar security properties, like collision resistance or whatever we want. And if we have that, then there are like generic transformations that transform this fixed length hash function to a full hash function that has arbitrary length input. And this is what's called a domain extension scheme. So here, a full hash function h is computed by this domain extension scheme D, which is some algorithm that uses a fixed length hash function f as a subroutine to evaluate h on some input x and produce y at the output. And of course, we want to do this in a way such that the full hash function h inherits any security that f might have. sorry, one more thing I wanted to say is basically that all practical hash functions that we are using are constructed that way, like using a domain extension scheme. So here's an example of a domain extension scheme, which is called the sponge construction, and it's used in the SHA-3 hash function standard. So here, for an input x, we split it up into chunks of r bits each. And if if x is not a multiple of r, we pad it in some particular way. And now we evaluate the hash function as follows, using using black box access to a fixed length function f that has input size equals output size. So first of all, we append a number of zeros to x1, the first chunk, and evaluate f on it. So now we XOR the second chunk into the first part of the output of f, and then we apply f again. And now we keep going like this until we have kind of processed all of our chunks. Here there are k of them. And then we apply f at least once more. Actually, one can generalize this by applying by generating a longer output. But here I've just taken the simplest case. We evaluate f once more to generate the actual output y. Okay, so after we have kind of an overview of what a hash function is, how it's constructed, at least like kind of on the high level, and about its security properties, let me go into a bit more detail where in cryptography hash functions are used. So in the NIST competition for standardization of both quantum cryptographic schemes, there are basically two kinds of schemes that are standardized: signatures and key encapsulation mechanisms, which are precursors for public key encryption. And on the signature side, first of all signature schemes use this hash and sign paradigm. This is basically the only efficient thing to do, at least that we know of, I think. By the way, if anybody is more of an expert than I am on any of the topics that I talk about, then I'm happy to be corrected. And so some digital signature schemes that are take part in the NIST competition use this generic transformation that I already mentioned, the so-called Fiat Shamir transformation. And I will talk about this more later, right? And then there's another subset, which is our so-called hash-based signatures. And here, basically, the hash function security is the only assumption that goes into the construction of these digital signature schemes. Also, for key encapsulation, there's kind of different degrees of involvement of a hash function in these schemes. So first of all, as far as I understand, all key encapsulation mechanisms use a hash-based key derivation function. So basically, the final key is hashed again to avert a certain class of attacks. And some key encapsulation mechanisms, actually, I'm not exactly sure whether all that partake in this all. I see. Okay. So basically, it seems like all key encapsulation mechanisms that are submitted to the NIST competition, so not some, as I wrote on the slide, use the so-called Fujisaki Okamoto transformation, or at least one of its variants, which is a generic transformation that upgrades the security of public key encryption schemes to achieve the strong notion of chosen ciphertext security. Okay, so after we have basically an overview over what a hash function is and how it is used, let's have a look at the at the meta strategies of how to attack hash functions. So as we have seen, if we want to construct a cryptographic scheme, what we have to do is we have to come up with a fixed length hash function. Then we have to apply a domain extension scheme, and the resulting full hash function we can use in a cryptographic scheme. So this kind of gives three classes of attack depending on which level of detail of the construction of the hash function we look at. First of all, what we could do is we could apply the nuts and bolts of the construction of a fixed length hash function. So there's like some operations happening, some non-linear operations that make this fixed-length hash function intractable, we think. But one can try to attack it. Another option is we could regard the fixed-length hash function as kind of a black box that has all the security properties we like. But then, we could try to attack the domain extension scheme. So it's supposed to ensure that the hash function h inherits all the important properties of f, but maybe it doesn't. So maybe we can find an attack that exploits some insufficiency there. And finally, we could just regard the hash function as something monolithic, just a function that has all the security properties we like, and we could try to attack the way it is used in cryptographic schemes. So now I would like to give an example for all of these, or one or more examples for each of them. So first of all, if you want to attack the low-level structure, that's actually something I know very little about. But I was pointed to a paper that appeared just a couple of days ago on ePrint, which improves classical differential cryptanalysis on hash functions using quantum algorithms. So this is something one could read if one was interested in figuring this out. Basically, on the second level, where we try to attack the domain extension scheme, there, for example, in a paper by Chris and Andy and some others, which is actually about provable security of the sponge construction, there's also an attack presented on the sponge construction, and it doesn't use anything about the structure of the fixed length function f here, but what it does is it finds a collision of the whole hash function h by essentially just finding a collision of this low-level function, of the fixed length function. You can see this, right? Like the standard quantum collision finding algorithm has complexity 2 to the n over 3. If you search in an n-bit a search room, if the function has an n-bit codomain, and here there's the number 2 to the c over 3. So c is exactly the size of the second part of the output of f. So it's enough to find a collision of the second part of the output of f to find a collision of the whole domain extension scheme. Now, finally, if we want to attack the use of this hash function as a monolithic object used in a cryptographic scheme, that's basically what the rest of this talk will be about. Okay, so basically the two examples that I want to talk about are these two generic transformations that are used a lot in post-quantum crypto. So to do that, I would like to first explain the two transformations. The Fiat Shamir transformation, it takes a certain kind of interactive proof system and makes it non-interactive. So this certain kind is a so-called sigma protocol, which works as follows. So we have a prover and a verifier. And the prover wants to prove some statement x, the truth of some statement x. The verifier doesn't believe it and asks the prover to prove it. And how do they do it? They do it by running an interactive protocol. And the interactive protocol works like this at a high level. So the prover sends some message A to the verifier. Now the verifier chooses a random challenge C from some challenge set independently of A. And finally, the prover sends some response R. And now if everything went right, if this is a good sigma protocol, now the verifier should be convinced of the truth of the statement X. And note that in general, right, maybe it's difficult to determine whether X is true or not. And maybe the verifier is doesn't have sufficient computational power to do that, but maybe the prover knows it, and he can prove it to the verifier without the verifier being able to compute the solution himself. This property that the prover chooses the challenge at random is called public coin, and basically the security property that we want, or one of the security properties which basically lets the verifier conclude the truth of X, is called soundness. Now the Fiat Shamir transformation, as I said, takes such a protocol and makes it non-interactive. So how does this work? Basically, the idea is if we work in the random oracle model, let's imagine we work in the random oracle model for a second. So now we have this random function. So whatever input we provide it with, it maps it to an independently uniformly random output. So what we can do now is we can replace the challenge C that was previously sampled by the verifier by the random oracle, or the hash function, evaluated at the concatenation of the statement X and the first message A. So why does this work? Why is this a meaningful transformation? So basically, you can see that what happens is that the hash function replaces the interaction as an enforcer of time order. So the reason why we need to do this in an interactive way is that we need to force the prover to first commit to sending some message A, and afterwards we provide him with a random challenge, as if we are the verifier. And now basically the intractability of H should ensure that the only way for the prover to come up with a pair A and C that is consistent with the hash function is by first choosing A and then inputting it into the hash function and obtaining C. Okay, so we will talk about the security of this later. Let me first show how it can be used to construct digital signature schemes. So now, basically what we have is we have a very similar structure. We still have this non-interactive proof system obtained from the Fiat Shamir transformation. But now we are using a particular class of statements where it's efficient to sample pairs of statements and witnesses. So the witness is something where you can, that basically lets you efficiently verify that the statement X is true. And now what happens is that that's basically what is used as a public secret key pair. So there's this witness, that's the secret key, that lets the prover determine the truth of the statement X and therefore also prove it. And the only thing that we have to do now is in this hash function that generates the challenge C, we have to include the message in the input. So that kind of indivisibly connects the message with the truth, with the proof itself of the statement. And if there's a number of additional properties that that proof system has, then basically the verifier can be sure that whoever generated this proof actually had the witness, aka the secret key, and intended to send the message M. So that's how a Fiat Shamir non-interactive proof system can be used to construct a digital signature scheme. Okay, before talking about attacks, let me quickly also introduce the other transformation, which is called Fujisaki Okamoto transformation. So here we have a weakly secure public key encryption scheme, and we want to upgrade its security. So a generic public key encryption scheme, it takes as input a message M and some random tape R, or a random string R, and it generates a ciphertext C using the public key. And the decryption function, of course, takes the ciphertext C as an input and recovers the message M. Now, if this scheme is not sufficiently secure for our standards, if it doesn't have chosen ciphertext security, we can apply this Fujisaki Okamoto transformation. So what it does is it de-randomizes the encryption scheme first, and after that it adds an additional hashing and authentication step to ensure this chosen ciphertext security, basically to decrease the utility of a decryption oracle. So how does this work? So first of all, we use a hash function, again, basically thinking about it as a random function, to replace the randomness input of the encryption function. So now, as you can see, this is a deterministic encryption scheme, right? Because the random input is determined deterministically from the message M. And now that we have a deterministic scheme, we can add this authentication step, which works as follows. So now we're talking about a key encapsulation scheme. That's why these algorithms have different names. And let's look at this decapsulation functionality first. So what does it do? It takes a ciphertext, and then it decrypts it to obtain M. But then it actually re-encrypts M using the correct randomness that the encryption should have used. And if it doesn't get you back the ciphertext C, then it basically refuses to work. But if this was an honestly generated, deterministically generated ciphertext, then it outputs the hash of M using a different hash function. And now that we're talking about a key encapsulation mechanism, the encapsulation function also outputs this hash. So now we have a functionality that basically generates a shared secret key if everything goes right. Okay. So now that we know these two transformations, let us look at attacks on these transformations. So first of all, about the Fiat Shamir transformation. So if we work in the quantum random oracle model, then there are security proofs since recently. So we were able to prove that if we have a dishonest prover, so remember that we are talking about this proof system. So in this non-interactive version that is results from the Fiat Shamir transformation, if we have a dishonest prover that makes Q queries to the random oracle, quantum queries to the random oracle that models our hash function, then such an attacker cannot prove a wrong statement with higher probability than a factor of order Q squared larger than the optimal success probability in the interactive version. So basically in the parent scheme, that's much simpler or much more intuitively secure. Okay, so this is a nice theorem, and independently, this was also proven by Liu and Jandry with a looser bound. So one natural question is, of course, can we find a matching attack that shows that basically we cannot do better, that this is the best we can have? And this turns out to be true. And to understand this attack, we need to talk about zero knowledge. So such a sigma protocol, we've seen this before, right? It can have a certain property which is called zero knowledge. And to understand this, we first have to observe that the prover sends these messages A and R, and supposedly he is using some information to generate them that the verifier doesn't have. So in some sense, the verifier learns something from this transcript, right? At least he learns the fact that X is true. And the idea of zero knowledge is now that this is exactly what he can learn. So basically, that he cannot learn anything else but the truth of the statement X. So formally, we need to formalize this in some way. And the way we formalize this is by requiring that transcripts can be simulated, without additional information except the information that X is true. So a bit more formally, but still informal, this can be put like this. So a sigma protocol, sigma, is honest verifier zero knowledge. If there exists a simulator, this would be an efficient algorithm, that for all true statements X can sample transcripts, fake transcripts ACR, such that these are indistinguishable from an actual transcript in the protocol. Okay, so now, how can this be, right? We have this proof system. It's supposed to to be hard, or maybe the statements are hard to prove in general. But now what happens here is that S does not have to respect this time order of generating A first and then receiving C and then generating R. So that's basically the advantage that the simulator S has over the actual proof system. But now this is great, right? We have this machine. It generates valid transcripts because the verification algorithm is kind of something that everybody can apply. So if they're supposed to be indistinguishable, then they have to be valid, these transcripts. And because we modeled at least we did model the hash function as a random oracle, with a small probability, actually this transcript will look like the transcript from the Fiat Shamir transformation, right? Because with some small probability, the hash of x comma a is indeed equal to C, the output of the simulator. But that's great, because what we can do now is we can Grover search for such a transcript. How does this work? So S is, of course, publicly available. It's efficient and randomized. So let's explicitly take this randomness input into account. So S takes as input a statement X that is to be proved, and a randomness input row, and it generates this transcript. And now we define a function that depends on H and X, and it takes as input a random string row for the simulator, and it outputs 1 whenever the simulator produces one of our desirable transcripts, right? And it produces a transcript such that it's compatible with the hash function. And note that this function can be computed using a single query to H, if it's a random oracle, and if it's a hash function, it can compute it, of course. So now this leads us to this kind of more or less straightforward Grover search strategy. So if we have a Sigma protocol that has perfect honest verifier zero knowledge, and a property called special soundness on top of it, and some mild additional properties where I'm pretty sure that they are not strictly necessary if you put a bit more work into proving things. Then there exists a quantum polynomial time attacker that makes Q queries to H, if it's a random function at least. That succeeds in breaking the Fiat Shamir transformation of sigma with probability q squared over q squared times the soundness error of sigma. Right, and this is essentially because this special soundness property, it ensures that the soundness error is indeed.
Sorry. This was exactly the question I wanted to ask.
Okay, so. Yeah, so this ensures that this soundness error is actually so small that that actually the Grover search gives us the required advantage. Now, how relevant is this attack? So. Sigma protocols that are used for Fiat Shamir signatures have at least some form of honest verifier zero knowledge, because that's what is used to prove chosen ciphertext security. And they also have some form of special soundness or a similar property that has kind of a similar effect. And therefore, I expect this at least to be kind of somewhat relevant in practice. Okay, so now that we, that's great, right? Did we completely figure out Fiat Shamir now? And the answer is, of course, no. Because we worked in the quantum random oracle model. And so in the quantum random oracle model, I think we figured pretty much, we pretty much figured it out. Of course, there's some cases that our attack doesn't cover, but it should be fairly general. But the problem is that the random oracle model cannot be instantiated. So this was, in the classical case, already proven in 98 by Kennedy, Goldreich, and Halevi. So there exists a digital signature scheme that uses a hash function. If this hash function is modeled as a random oracle, then this digital signature scheme is secure. But it's insecure whenever I use any efficiently computable function, h. So that's, of course, a bit discouraging. And this was later generalized to the quantum random oracle case by Fang Song and Edward Eaton. Basically by proving that the separation schemes are also secure in the quantum random oracle model. So even though the quantum random oracle model gives the attacker more power, the separation still holds up. This, of course, points to the fact that there might be better attacks than the one that doesn't use any structural property of the hash function, no matter what hash function we choose. Okay, now let's come back in the last 5 minutes or so to the Fujisaki Okamoto transformation. So here is it again. Remember that we started by de-randomizing the encryption scheme by replacing the randomness by a hash function, and then we added this authentication step by re-encryption and hashed the output. So let's denote these three schemes, the initial one by pi, the intermediate one by pi prime, and the final one by pi double prime. So for proof of post-quantum security of this transformation, again, usually the hash functions h and h prime are modeled as random oracles. So what we want is we want to take a scheme pi that is in CCA secure, or even weaker one-way CPA. But let's look at in CPA as a starting point here. And now for the deterministic intermediate step, we want to prove one-way CPA from using the int CPA property of pi. And finally, we want chosen ciphertext security and CCA secure key encapsulation for pi double prime. Now, in this paper by Andy and others, there's a tight reduction for the final step provided. Actually, so I didn't introduce this transformation. It's a slight variant of the one that I've shown for simplicity. But one can modify it a little bit, and then one gets a tight reduction. But for the first step, we only have a lossy reduction. And actually, in the quantum random oracle model proof, there is a multiplicative loss of the number of queries that an attacker in this pi prime scheme here, sorry, let me go back, makes to this hash function h that's used to de-randomize, that we model as a random oracle. Now, this implication is tight in the classical ROM, so that's kind of annoying. And there's no attack known that exploits this gap. So can we apply our vanilla approach, Grover? Probably not. I would say, because basically what it usually can do is it can boost an advantage of Q for Q queries that exists classically to Q squared that in the quantum setting, and we don't have any classical advantage here. Now the question is, of course, can we apply any other algorithm? And this is exactly the question that Dan asked in an email that was sent to the participants of the program. Just another remark. So, of course, here the same caveat applies with respect to the quantum random oracle model as well. Let's take a little bit more of a closer look at what's the problem. So, right, we want to assume that we have what goes wrong in the reduction. So basically, we want to assume that we have an attacker that breaks the one-wayness of this scheme. So it takes C and comes up with a message M for a C that's generated from a random message M. Now we want to use this to break int CPA of this scheme here. The problem is, in the int CPA game, what we can choose as attacker is this message M, or at least we can provide two messages, and one of them is chosen at random and encrypted. But we have no control whatsoever over the randomness R. And for these encryption schemes in general, one cannot see from the ciphertext C which randomness R was used. So now basically the problem is that if we want to use this attacker as a black box, we would need to provide him with a ciphertext C together with an oracle H that's consistent with it. So basically with an oracle H such that H of M is equal to R, whatever R was used to generate the challenge ciphertext. And this is something we can't do because we don't know R. And why is this not a problem classically? So classically what we can do is we can choose 2 random messages as challenge. And now we can run this guy, and even though we provide him with an inconsistent oracle, at some point there needs to be a query where he for the first time queries the message M. And note that he can only query the message M that corresponds to the ciphertext he received, because the other one is independently random, so he doesn't know. He will only query it with negligible probability. So this is how we can extract the message M and basically win the CPA game. But in the quantum setting, although it seems like for a fixed classical ciphertext C that comes from a fixed message M, it doesn't make sense to make superposition queries. We have no way of extracting this message M because in general the adversary could make superposition queries. So we just don't know how to basically extract it when we provide the adversary with an inconsistent oracle. Okay, this is basically all I wanted to say. So what we talked about is that hash functions are used essentially everywhere in crypto, so we really need to subject them to some quantum cryptanalysis. And there, I showed basically how there's this different levels of detail where you can attack. When looking at attacks of the application in cryptographic schemes, there are some open problems, especially regarding this Fujisaki Okamoto transformation. One can only expect polynomial advantages because there are reductions that preclude anything beyond that. But this is still important, at least if we kind of take quantum cryptanalysis seriously, in the sense that we expect it to be used for parameter choice at some point, then polynomial factors are extremely important. Thanks.
We have time for a couple of questions. Okay, now let's name.
Did you want to ask? Oh,
Is there a question? Yes.
So the key derivation function you mentioned, what kind of properties do you need for the hash function to make that work?
I think that usually the proofs are in the random oracle model. I don't know. Probably we don't know how to do with less.
Any more questions?